All right, we're ready to talk about theoretical things. Theoretical semiconductor stuff, for which I'm going to try, as best I can, not to leave you behind. We'll see. This is like, last week felt like 2 weeks. For whatever reason, I don't know. I kept thinking it was the second week of class because it was such a long week. So I keep feeling like this should be the third, but I know it's not. I know this is the third time we've met. So we haven't done anything yet in here. In my other class, we're getting ready to have a test on Friday, but in here we haven't done anything other than talk a little bit about crystals. And we're still there, actually. We're still talking about the structure of semiconductor material. So what we're going to talk about today is how and why the structure ends up the way it is, basically. Why atomic structure is affected by energy, because really energy affects, it's basically the basis of why you're an electrical engineer, is energy. You put energy in, you get energy out. You should hopefully get, if whatever energy you put in, you should get that amount of energy out of a system unless it's being used within the system. So semiconductor devices are the same way. They are structured so that they use energy to determine kind of where the atoms end up. So we all know, because you haven't had physics, but everybody pretty much has heard of the conservation of energy. Everything has some kind of energy in it. You, me, the room, everything. There's a lot of different kinds of energy. There's kinetic and potential and chemical and heat and mass and all those things, and most of them we don't care about in here. But one of the things that becomes very, very important here is the idea of something called thermal equilibrium. Thermal equilibrium is the point at which a system gets to, based on temperature, so you have to hold the temperature constant. If you increase the temperature of a system, you're adding energy, so you have to leave the temperature constant. But if you leave the temperature constant for a particular system, everything will kind of fall into its lowest energy state. So it's kind of like if you put a bunch of people in a really hot room with a television and they don't want to move around, so they just kind of all sink into chairs and sit and don't move. And then if nobody disturbs them, they pretty much stay there and then they fall asleep. At least that's what my kids do. So in here, the only two kinds of energy we're worried about really is potential energy, which is just energy that's sitting there waiting to do something, and kinetic energy, which is energy in motion. Was that my device that made noise or somebody else's? Okay, just making sure, because sometimes we get weird things that happen here. So when atoms arrange themselves into some kind of structure, it occurs to minimize the energy. Whatever structure they end up with is going to be the structure that minimizes the total energy in the system, and so that everything is kind of at its lowest energy level. So remember when we talked about simple cubic crystals and said, well, those are not very common. And the reason they're not very common is because there's a big gap in the middle, and that generally will drive some kind of potential energy to push the structure into something else. It might twist so that the atoms get closer together. So that's one of those driving mechanisms that determines how things are structured. So the type of atoms that are used in creating a crystal determines what arrangement leads to minimal energy. The environment in which a solid forms determines the structure. For example, carbon forms two completely different types of structure. It forms graphite, which are sheets of kind of hexagonal rings, and that's its normal form that it does. Usually when it's under standard conditions and everything is kind of relaxed, it makes these rings of really soft material, and basically when you're writing with a pencil, you're just scraping off carbon rings. But if you put carbon in a different situation where there's high pressure and temperature and not much space, you get a diamond. And that's why you get diamonds out of carbon deep in the earth, but not at the surface, because it requires the temperature and the pressure and the constriction of environment. Yes?
So with carbon fiber, what's up with that?
No idea. Because this ain't a carbon class.
Yeah.
This is a silicon class. But that is a good question, and I want to find out more about it now that you asked. But we're going to talk about something chemical right now. And we're going to talk about something you may already know about, which is the Bohr atomic model. It is something that is kind of covered whenever you talk about structures of molecules and atoms. But Niels Bohr was a physicist, and he won the Nobel Prize in 1922 because he made some really good contributions in understanding how atomic structures work. His idea was that electrons orbit at certain levels. So they have stable orbits at discrete energy levels around a nucleus. And if an electron goes to a higher energy level, you have to put energy in to get that to happen. And if it moves to a lower energy level, then energy is released. And his ideas were good, reasonable. They're not exactly right. So the actual model is kind of primitive and it's been revised, but we still use it because it does give the idea that electrons can only exist at certain places. They can't exist everywhere around a nucleus, only at certain energy levels. What we know now is that they don't go around like this, like planets. They actually just move within that energy level at completely random ways. So they don't actually have any particular circular way that they're going to move. But his atomic model basically looks something like this, where, and don't worry about the K and the L and the M, that's inconsequential to what we're talking about today. But the idea was you have the nucleus, and then you have a certain number of electrons at the first energy level and a certain number of electrons at the next, and so forth, and you can fit more electrons at each outer level. And that's pretty much true. Silicon and germanium each have 4 electrons at their outer energy level. So does carbon, but silicon and germanium are what we're talking about today, not carbon. So when we talk about silicon and germanium in here, we're only going to talk about the electrons in the outer valence shell. We're not going to talk about anything inside. So silicon, it has actually 4 electrons in the valence shell and then 2 other levels that we will not consider. And then germanium has even more electrons to it because it's further down in the periodic table. Again, we're going to completely ignore all the inner energy levels and just worry about the 4 valence electrons. So, how does this work? Well, basically atoms form structures in order to fill valence shells. The valence shell that we are concerned with both silicon and germanium, wants to have 8 electrons in it to be full, and they only have 4. So they're going to do something in order to become stable and to make each atom think that it has 8, even when it doesn't. And I know that they don't think, and I know that but that's just the way I think about it, is that, they feel relaxed because all the electrons are there, and that basically lowers the potential energy. So there's a couple of ways that atoms combine in order to fill valence shells. Ionic bonding is one way, and usually that's atoms from 2 opposite ends of the periodic table that either lack 1 or 2 electrons or need 1 or 2 electrons, and sodium chloride is a really good example. You'll notice that one of the electrons from sodium goes over and fills up the valence shell for chlorine. They stay together. Sodium kind of thinks it has no electrons in the outer shell, which is great, and chlorine thinks that it's full, and that's stable too. But those are opposite ends of the periodic table, and that's not where we reside with silicon or germanium. We're actually right in the middle. So the other way that bonding occurs is covalent bonding. Covalent bonding is when you get atoms from the middle of the periodic table, and they share electrons. And in the sharing of electrons, they feel like they have full valence shells. So silicon, germanium, and every other kind of semiconductor we make does this. It makes this structure that shares electrons in the valence shell and makes it as if the outer shell is full. So that's one thing that happens, but that's not the whole story. The sharing of electrons we'll talk about in a minute, but the other thing that happens is there has got to be some way of determining how far apart the atoms are, because there is a point at which they stop. They don't just smash into each other. There is a distance between atoms, and that distance is actually determined by the balance of potential energies between pulling them together and pushing them apart. So if we use hydrogen as an example, it is actually a covalent type of bonding material. It's kind of unusual because it's off by itself, but it only has one electron in the valence shell. So if you bring hydrogen together with another hydrogen, they make H2, and that's a pretty common thing that happens. So what happens with hydrogen, there's one valence electron in the outer shell. For that initial outer shell, 2 electrons would be the maximum it could hold. So hydrogen atoms covalently bond with each other, and they form H2. So they just come together and they share those 2 electrons, and each atom is acting as if it has 2 electrons in the outer shell, even though they're sharing it. The distance that they come to is a trade-off between how they are kind of working with the energy. So if we look at the energy and how it works, you'll notice that way out here, you have a pretty far distance apart and not a lot of potential energy. So here the potential energy is approximately 0. So basically they're not interacting at all. But there is, as they get closer together, more and more potential energy that starts pulling them together. And they finally get to a point where that energy is the lowest it can be. It's actually negative. But if they came any closer together, then they would actually have energy pushing them apart. So the point at which they stop moving together and they kind of settle is basically the interatomic distance between 2 atoms. And that actually is the observed distance that they see in picometers, it looks. So that's basically what's determining. It's just energy. It's just energy. They move together. They come to a point where everything's kind of balanced, kind of like personal space. You know, you don't want to be too close to somebody, but you don't want to be too far away if you like them. So what happens is you have a whole bunch of silicon atoms, and they each have 4 valence electrons, and they move together. So they all just come together, they start sharing, and each one has 8, especially the one in the center there. And then other silicon atoms come in and just start adding to the chain. And they make a very regular, very predictable structure, and very stable, because they've come together and gotten to the right interatomic distance, and they're sharing valence electrons. So silicon in this pattern is very comfortable. That's what we want. We want silicon like this, a nice pattern, nice stable structure, no extra energy pushing or pulling or anything like that. If we can get that to that point, we're getting started. However, nothing's perfect, and that's one of the problems with creating single crystal things. If we could make all semiconductor crystals perfect and no defects, that would be great. We do sometimes have defects that occur, and I'm going to tell you about all of them, and so you'll know what they are, because that's part of the course that you need to know. But anything we use in here will be perfect. I mean, we don't use much in here, but anything we talk about will be already perfect. So there are point defects that occur, and those are basically single points, single atoms that are either there or not there, or the wrong one, or whatever. There are line defects, which are two-dimensional defects that can occur, and then there are planar defects, which are kind of three-dimensional. They all affect the electrical characteristics of the semiconductor. So any one of these defects is going to mess up how electrons can flow in the material when they actually do flow. So, what kinds of defects do we have? Point defects, an empty spot where an atom should be. So like right there, that would be a point defect. Something called an interstitial. An interstitial is an atom where there is no empty spot. So it's like the opposite of a vacancy. It's an atom that came in and went into a spot that shouldn't be there, and it throws off everything around it. You'll notice that the other atoms around there have kind of shifted a little bit to accommodate it. And when that happens, that impedes the flow of electrons. There can be something, and this would be a line defect, it's called an edge dislocation. And that's basically where a whole line of atoms didn't line up right, and eventually below the defect, it starts to line up again, but it's got this big gap in the structure, and the gap in the structure is going to cause electrons not to be able to flow properly. Yes, back there.
Is this what they refer to as the silicon lottery? The silicon lottery? I've heard of that.
I don't know, because I've never actually heard of that.
I just know for like CPUs, some of them will perform better.
That can be, yes. Yeah, and that can, well, it can actually have something to do with that. If there are defects in the silicon, that will actually make them not, they can work, but may not work as well. Does that make sense? So yeah, if there are defects, they're not going to work right. Another type of defect, this is a planar one, and we've already actually seen this, is grain boundaries. We see those in polycrystalline structures. So we kind of already talked about polycrystalline structures and the fact that they were grain boundaries, and those just block the flow of current. So if there's any kind of a shift in the structure, that will just block electricity and it won't go at all. Another thing that can happen, and sometimes this is intentional and sometimes this is not intentional, is impurities. And crystals can contain impurities. That's a known fact. The picture on the right is a very famous crystal with impurities. That's actually the Hope Diamond. It's blue. It's blue because it's got boron in it. It's got boron. It's basically boron-doped carbon structure, diamond structure. So it's kind of like a semiconductor, except it doesn't work that way. But that's why, it's probably not why it's so famous. I think it's so famous because really awful things happen to the people that own it, from what I remember. But it is really big and really pretty, and the reason it is unusual is just because it has impurities. Impurities change the electrical characteristics of semiconductors, just like all this other stuff. Impurities can be unintentional or intentional. So unintentional impurities will have bad results. Intentional impurities have positive results. We'll talk a lot about intentional impurities when we get to that point. Unintentional impurities are a defect. Intentional impurities are necessity. So there's a kind of a difference depending on what the impurities are. So semiconductor devices have to have impurities in order to work, and we call that doping. And the ability to control that impurity concentration is why we can make so many devices out of semiconductor material, is because we can change what we put in it, we can change how much we put in it, we can design it from the beginning to have certain impurities that have certain characteristics, and that's basically why they're so cool. Another type of impurity would be something called a substitutional impurity. That's where you get a different atom as part of the lattice structure, and again, it's a different atom that you don't want. It's not a different atom that you wanted there. It's one that just ends up in there and makes itself known. The other way you can have also an impurity, you can have an interstitial impurity that's just there and kind of in the wrong place and just everything moves out of the way. So those are all the different things that you can do unintentionally to make semiconductors not work. Now this is what you do intentionally to make them work. So these are impurities that are intentional. Intentional impurities are added to intrinsic semiconductor material to make it whatever way we want to. We call pure semiconductor material intrinsic. It has very limited use. Actually, it has pretty much no use, because intrinsic semiconductor material has very little ability to actually conduct electricity. You have to have something out of balance in order to make it do anything. So impurities added to the semiconductor material increases a number of available charge carriers you can get. So we'll talk later about the types of charge carriers and how they are created and how they're put in there. But basically, what we have to do, the charge carriers in intrinsic semiconductor material are equally balanced. There are electrons in the conduction band, and then there's something we call holes in the valence band. We'll talk about that later. If we have the same number of each, there's really no mechanism to make current flow one way or the other. But semiconductor material to which we add impurities is called extrinsic. So intrinsic material is just pure semiconductor. Extrinsic is pretty much anything that's useful that has been doped. We add impurities when they're forming the crystal. So when they make the big melt of silicon, they basically put whatever impurities in there at that time and make the silicon crystal with the impurities already added. So there's two very general types of impurities. There are atoms from group 3 that have 3 valence electrons, and there are atoms from group 5 that have 5 valence electrons. And what ends up happening is basically if you add one type of material, you'll get one type of semiconductor. If you add the other, you'll get a different kind. So if you add atoms that have 3 valence electrons, we get something known as p-type material. Again, we will explain all this later. So this is just terminology. This is not anything, don't worry too much if it doesn't make sense. If we add 5 valence electrons, we have n-type material. Basically what this is doing, when you're adding 3 valence electrons, you're basically removing some of the available electrons from the structure, and you're creating gaps. And that's like creating holes. When you add atoms that have 5 valence electrons, you're adding extra electrons, and 4 of the valence electrons will bond and be part of the structure, and 1 of the electrons will just be, will feel like a fifth wheel and go off and do other things. So, in fact, when you add extra electrons this way, they have more energy because they're not so tightly bound to the structure. So we do this basically to make different types of material. The boules that they make are marked to let you know what kind of material they are and the orientation of the planes. Now, all semiconductors that are made are not still marked like this. It was kind of an early convention, but it's worth mentioning because it does kind of illustrate how the structure works. So you remember they made those long boules we talked about, and then I talked about how they made a flat on one side and it had a direction, but I hadn't talked about planes and directions anymore. But there is a flat that is perpendicular to the 110 direction. And then, depending on how it's been structured, the plane on the end will either be the 100 plane or the 111 plane, depending on how or what type of device is being made. So there's actually 4 kinds of materials that could be made. There could be N-type material that's oriented with the 100 face at the end, or there's P-type material that's that way, or there's N and P that have 111 at the end. And one of the ways I'm going to actually talk a little more about that with pictures in a second, just because it's really hard to visualize how this works. You've seen a unit cell, and the unit cell is already complicated, and then trying to visualize the different planes, I mean, it's hard for me. But I think I've got it pretty well at this point in my life. But anyway, the flat is ground on one side, and then when the wafer's cut, there's a flat piece on the bottom. And that flat piece on the bottom, no matter what kind it is going to be in the 110 direction. So it's going to be kind of parallel to that direction. And then, depending on what type of material you have, a secondary flat gives the type. So if there's no secondary flat, it's P-type with the 111 face going up. If there's a second flat at 90 degrees, it's P-type with 100 at the front. And you notice these have brackets, not parentheses, because it's a whole family of planes that's being considered, not just one. So that's why it's listed that way. The reason that there's 2 different ways of doing this is because MOSFET devices usually use 100 material, and BJT devices generally use 111 material. So depending on what you're making out of it, what type of device, you want a different orientation, because all semiconductor devices are basically etched. Everything is etched onto the surface. So the surface is really important. The surface density of atoms is important. The oxidation rate is important. So all of that is important depending on what type of material is made. Once this is done, you can also break the wafers into small pieces. And we talked about slicing them up with a diamond saw and the flat, and you guys passed around a flat circular. But once they are done, the wafers are broken into smaller pieces using cleaving. And I will actually show you a video in a minute about cleaving. But basically you use a scribe or a point, and you put pressure on the wafer, and it breaks along the bonds, which is really important. So if you bring in something and just smack it in the middle, it will break right along those bond lines. And a 100 wafer breaks at 90 degrees. It breaks at 90 degrees because that's basically how the bonds are structured. And what I'm going to do before I start, let's see, I'm going to talk about this last one first, and then I will do the next. The 111 breaks at 60 degree angles, so it breaks differently. If you actually try to break this, it will break into like pieces of pie. But you'll notice with both of them, they break along the bottom this way. Both of those different types, if I go backwards, you notice they both have a break down there. And you can actually start cleaving in the middle of the big flat, and it will split. And I'll show you that in a minute. I'm going to kind of move away from some of this stuff. For those of you watching a video, you won't be able to see some of this that I'm going to do. I'm just talking to the people who aren't here. So I have in my fancy bag here, this is actually supposed to be silicon. It's actually carbon. But we're not going to tell anybody that it's carbon. It's actually silicon. This side is the 110 plane. My little bonds always come apart here on me. So the 110 direction is going to be perpendicular to that. Go in there. There we go. So I kind of marked these sides. So what you can do is you can spin it. This is basically spinning on the 110 axis. That's the direction, and that's the flat at the bottom. And what you can do, and I'm going to pass this around so you can do it, but you can spin this and you can actually get it to orient either in diamonds, like if I look at it like this, now I see a bunch of triangles. And if I move it just a little bit more, I see a bunch of squares. So if you spin it along the axis that has the extra things and just turn it slowly, you may get to where it's easy to see the squares. The triangles are a little more difficult. And then sometimes you'll see a whole big tunnel. But that's what makes the difference in how they cleave them. All righty, I'm back again. Okay, there we go. All right, this is something that is on D2L that you can go and play with this as well. This is just a unit cell you can rotate. And the middle green plane is the 110 plane. So if I'm spinning this on my axis, this is actually where you get the triangles. And the 111 plane is that purple thing right over there. So that's kind of how it's oriented when it's like that. And then you can spin it, and when you spin it, eventually you will get to where you see squares. So those are the two ways the crystals are going to be oriented. They're either going to be oriented so that when they cleave, they've got all squares, or when you cleave them, it's got triangles, depending on if it's a 111 or a 100.